Hi and welcome. I'm trying to learn particle physics. Today, what caused cosmic inflation? And after we've done that, we're going to do standing yoga. And if you participate in the standing yoga, then it's already honest. What caused cosmic inflation? Cosmic inflation is the best theory we have to square the type of universe we see with a universe that began in a Big Bang. But we are still casting around for the trigger of this mysterious period of faster-than-light expansion. So cosmic inflation, what we'll probably explain here, explains why the universe is expanding. That's an idea of it. But it can't explain why the universe is expanding faster as the speed of light. They say it started with a Big Bang, but in truth it misfired. The universe began as a hot speck of energy and, for an instant, remained just that. Then it blew up. From this initial seed, trillions upon trillions of times smaller than an atom, everything suddenly ballooned into the gargantuan proportions of a tic-tac. In a mere fraction of a second, the universe expanded by nearly as many orders of magnitude as it would in the following 30.8 billion years. Okay, they're saying first the universe was for a little moment trillions upon trillions smaller than an atom. So trillion times smaller than an atom. And then it got the size of a tic-tac. And when it expanded, as the magnitudes bigger as it would follow the 13.8 billion afterwards. So they don't say it expanded as much as when in 13 billion years later it expanded by, let's say, 10 times as much. And it has expanded since then another 10 times. So it's multiplicated, not with real numbers or whatever. As hard as it might be to swallow, this burst of cosmological inflation, followed by a slower, tamer expansion, is the most sensible way to iron out wrinkles in the infant universe that otherwise would have left today's cosmos looking rather more lumpy and uneven than it does. I'm not even sure if I said anything there. It would have left today's cosmic looking rather more lumpy and uneven than it does. So if it would have not expanded, it would be everywhere lumpy and uneven. But there is something crucial missing from the story. What did the inflation? So what did the inflation? The most natural solution, given what we know about how fields and forces dictate the universe's workings, is to postulate an inflation, an energy field with dynamite properties. But what and where is it? So an inflation field with dynamite properties. We have an idea about what to look for. Maybe we mean with dynamite properties just that it is like dynamite explosive. So something which has properties like other explosive stuff is. We have an idea about what to look for. The inflation must be a scalar field. This is just a mathematical way of describing a field that acts in all directions, but whose strength can change over space and time. So scalar field means in math that it is expanding in all directions, but the strength is changing. The further it expands, there's less power or more, whatever, and over time. So a minute later, it has less power at another side. One way to think about it is like a weather map of air pressure. Air pressure varies depending on the location and day of a forecast, but unlike wind strength, say it is directionless. So wind is blowing in one direction, such as hot or low pressure in the air pressure is not blowing, it is just there, but nevertheless on the next day it might be somewhere else and it has changed. What we are searching for then is an invisible fluid-like substance. So it is invisible and fluid-like. One that suffuses all of space and has the potential to influence everything in it. So it suffuses all of space and influences it. Or at least it did. The inflation field must have generated something akin to extreme anti-gravity, a cosmic urge that blew up the fabric of space-time but quickly lost its impetus, I don't know what it means, to the point at which its influence essentially disappeared and normal expansion resumed. Okay, the hypothetical, I don't think it's proven, inflation field generated something like anti-gravity. That blew up the space-time fabric. In principle, there is nothing stopping us from tracking an invisible energy field that has lain low for 13.8 billion years. It is what particle physicists do with machines such as the Large Hadron Collider. They isolate a little pocket of a field, otherwise known as a particle, by smashing other particles together to generate a momentary flash of energy. So we're isolating a little pocket of a field or of a particle. We discovered some of the most elusive fundamental particles, such as the quarks, in this way. But those particles aren't associated with scalar fields, and in the decades following the proposal of inflation, our best particle colliders failed to find anything that was, until in 2012, the Higgs boson finally showed up. So we found the Higgs boson, and the idea is to have with the Higgs boson to find out how it is maybe doing the scalar field with the inflation field. You can see where this is going. Might the Higgs actually be the inflation in another guise? If the Higgs gives inertia to particles, says Juan Garcia Bellido at the Autonomous University of Madrid, can it give inertia to the entire universe? So the Higgs is giving, probably, I don't know, inertia to the particles. Is it giving now maybe to the whole universe? The inertia, I don't know what inertia means. At first glance, the two are different in a crucial way. Unlike the inflation, some of the Higgs field remains when it falls into its lowest energy state. So the Higgs field itself remains. It is precisely this sticky residue that manifests as the property of mass for other fundamental particles. It is precisely this sticky residue, I don't know what the word means, that manifests as the property of mass for other fundamental particles. So that the Higgs field stays even after having reached its lowest state of energy, makes it able that the other particles can have their property of the fundamental mass property manifests as the property of mass for other fundamental particles. But that is in today's universe. As physicists Fedor Bezrukov and Mikhail Shaposhnikov at the Swiss Federal Institute of Technology in Lausanne, EPFL, realized, tweak the Higgs properties just a little, and in the moment following the Big Bang, it could have mustered enough force to flood the still minuscule cosmos with inflationary gusto. Okay, if the Higgs properties tweaked in the moment following the Big Bang, it could have been enough to be in the whole universe. That involves filling the Higgs potential curve. Essentially, the energy a particle needs in order to have a certain effect, such as bestowing mass on other particles. So the Higgs boson might have driven cosmic inflation when the early universe ballooned. It depends on the Higgs potential curve, which describes the energy a particle or field needs to produce a certain effect. Effect, energy. The effect goes from big to low. The bottom of the Higgs potential curve is shaped like the base of a champagne bottle. So even when background energy is low, as it is nowadays, the particle sits in a position that means it gives other particles mass. So the background energy is low, but the Higgs is still in a position to give other particles mass. But if the Higgs potential flattens out at the sides, then when there is more background energy, as there was during the earliest moments of the universe, its field would be supercharged. This could have generated enough anti-gravity to drive cosmic inflation. Okay. If it flattens out the Higgs background radiation or the Higgs background energy, then there was more during the Big Bang or after the Big Bang, and the field would have when there was more background energy, as there was during the earliest moments of the universe. So if the potential of the Higgs is somehow widened or something, or flattened, then there was more backward energy of the Higgs at the beginning of the universe as there was. Now, when there is today more backward energy of the Higgs as there was in the earliest moments of the universe, and the field would be supercharged now, and that could have generated enough, it's another past, whatever, it's just theoretical, so it's one way or the other, whatever, it doesn't really matter, it's just theoretical thinking. Okay, that was for particle physics part. If you were here for particle physics, you can calculate this the next part, where you will read on at that place with Higgs, and is it doing that inflation field, which is somehow expanding the universe faster than the speed of light or whatever. If you stay here and participate in this, then you will miss that. The feet are standing together, believe in the arms up. Out and down. In and up. Out and down. Or down to the side. In and up. Or to the other side. In and up. Make an inch of space between the feet. Out and the side. In and up. Out to tiptoes. And out and sink a bit down. In and up. Out again down. In and up. Out and down. In and up. Out and lean onto the knees. Breathe in. Out, make a round back. In middle. Out the belly back. In middle. Out. In middle. Out the belly. Middle. Out, come off around, back up, back at the top of the good shoulder down. And breathe in the arms up, come up on the tiptoes. And out and down, feet together. Breathe in. Stretch only the left leg, bend the right one. And change, stretch the right leg. Middle and down. Lift the right hand up to the sky, bend the left knee, look to the sky. Hand again down. Lift the left hand up, bend the right knee, look to the sky. Hand down. Make a hand with space between the feet. Shift the weight of the heels and breathe in and go down. And out and come up. In and down. Out and up. Take hold on the elbows and gently rock from side to side. Feet together. Breathe in halfway up with straight back. Out and down. In halfway up, straight back. Out and down. Breathe in, come up with the hands. Then again down. The toes are pointing to the outside. Breathe in the arms up. And breathe out and sink down. Place the elbows against the insides of the knees. Breathe in and straighten up. And out and come with the back up. Breathe in. And out and down. Breathe in, straighten up. And out, come in one straight line upwards. Hands again down. Breathe in the arms up. Out, sink again down. Breathe in, straighten up. And breathe out, come with the back up. Breathe again in. And out and down. Breathe in, straighten up. And out, come in one straight line upwards. Hands again down. The next exercise can go into the back, legs apart, breathe in, arms up. And out, lean the front of a straight back, breathe out. This can go into the back, make a round back, and breathe in and come with the crown of the head up. And out. And now time, breathe in. Out, bend the front of the low leg, the straight back, the round back, and breathe in and come to the front of the head again. Head, back. And have the feet standing together. Intertwine the fingers behind the back, over to one side, legs apart. Pull up, breathe in. And out, bring the head over to the side of the head, chin down over the clavicle, and pull the opposing shoulder in and down. Breathe in, lift the gaze, turn it over to the other side. Hands over to the other side, breathe in. Out, chin down onto the clavicle, pull the arm and the shoulder down. Breathe in, lift the gaze, back into the leg. Have the feet sink together, breathe in the arms up. And lean back, drop the shoulder blades together, in and up, intertwine the fingers to each side. Breathe out, reach your front, hold the back. In and up, change the direction. Out and in front, in and up. Lean back with long arms, draw shoulder blades together, elbows down, in and up. Out and back with long arms, shoulder blades together. Arms down, in and up. Out and down. In the arms up. Out and down. In and up. Bring my hands to touch and love and learn to heart center. That was the standing yoga. I thank you very much and until next time.